Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this video, we're going to be building off the last one where we were talking about kind of the concepts of forecasting and how we forecast the weather. And this one, we're going to be putting that into practice. We were going from the theory of forecasting to the application of forecasting. So in this one, we're going to be talking about some of the tools, the methods that they use to forecast. And this should be a bit of a shorter video here. So let's go ahead and dive on into it. So once a meteorologist has thoroughly reviewed the current weather and ascertained what processes are producing it, forecaster can begin to look into the future. Forecasting, right? That's the goal here. Forecasters typically use what we call the forecast funnel. Typically, it kind of looks like what you see here. Forecast funnel is this concept that focuses the forecaster's attention first on the large scale processes, and then you kind of step into increasingly smaller scales. Numerical weather prediction models are basically computer simulations of the atmosphere. We kind of talked about those a little bit in the last video. These models provide the foundation of the weather forecast. The models use an analysis of the current weather as a starting point, the initialization, and then project the state of the atmosphere into the future. Models use complicated physics and fluid dynamics equations that require supercomputers to solve them. In addition to the numerical forecasts or numerical weather prediction models, we talked about those earlier, forecasters are going to draw on conceptual models, experience, and research to produce a valid forecast. Forecaster will then conduct a thorough review of the output of these models. At times, the models yield different results, and in these circumstances, forecasters try to determine what's going to give the best performance for a given situation, or they'll seek a consensus solution. Computer models and other weather data are viewable on the AWIPS workstation. We'll talk about what AWIPS is here in just a couple of slides. The main graphical interface has the ability to show several windows with different data, and these can be switched back and forth to kind of develop a forecast. So when forecasts are being issued, so the National Weather Service issues a comprehensive package of forecast products to support a variety of users twice a day. In addition, a late morning and evening update are typically issued. Additional updates are produced as conditions warrant. Although text forecasts have been the primary means of product dissemination for many years, National Weather Service has converted many of its forecast products to a digital gridded format, kind of like what you're seeing in this GIF that's playing out on the slide with us here. Each of the 123 National Weather Service forecast offices send their gridded forecasts to the national server to be compiled in the National Digital Forecast Database, or NDFD. The NDFD is a national gridded forecast database of sensible weather elements, including maximum and minimum temperature, humidity, cloud cover, probability of precipitation, weather type, wind direction, and wind speed, produced by local forecast offices. Most of the primary forecast products issued by the National Weather Service, including those for the public, fire weather, and marine users, originate via this gridded forecast database. Once a meteorologist has thoroughly reviewed the weather situation and conceptualized this forecast, it's time to make a forecast. Forecasters are going to write an area forecast discussion, or AFD, that has a narrative text product that explains the meteorological reasoning behind the forecasts. The AFD was originally intended as a coordination tool between adjacent forecast offices, but it's now evolved into kind of a communication tool for end users like us, including local meteorologists, the media, emergency managers, weather spotters, and the public. So you can see this is one that I pulled as I was basically starting the lecture here. So you can see it kind of mid-afternoon on April the 30th, 2023. And this is for the Twin Cities Chanhassen station. So you can see chance for some light rain showers this afternoon in the west central Wisconsin and far east central Minnesota. Some snow could mix in again tonight in Wisconsin. Gusty winds up to 50 miles per hour continue this afternoon and evening, mainly in western Minnesota. Warmer and drier to start the work week. Elevated fire weather conditions Monday with continued gusty weather and a low humidity. And then they go into a bit deeper of an explanation, as you see kind of going off the picture here. Now, let's kind of talk about some of the tools that we're using here. We're going to talk about radar on our next, is the next one here. So during World War II, it was pretty quickly discovered that precipitation presented targets on radar display. Radar is basically just an acronym, radio detection and ranging. Um, so what happened was they basically saw precipitation presented targets on these radar displays and frequently prevented the full utilization of radar systems for the intended purpose, military applications. Enemy aircraft, becoming aware of this limitation, could plan their approaches on Allied radar systems from directions that precipitation was occurring. The enemy also used finely cut strips of metal called window or chaff to confuse radar operators with false signals or to cover the approach of their aircraft. The effect was quite similar to that caused by precipitation, although it didn't generally cover as large of an area. From another perspective, radar observations of precipitation areas were frequently of significant value in military operations, and meteorological officers soon discovered a new tool with which they could increase the accuracy of short-term forecasts. Unfortunately, due to the scarcity of equipment, the security of the new technology, and the dedication of existing equipment to direct military application, radar meteorology development was pretty slow for the first few years after the war and during the war. At the conclusion of the war, and after security restrictions were relaxed, the new science of radar meteorology started to evolve or emerge. So, how does it work? Well, radar creates a very strong, roughly 1 megawatt pulse of electromagnetic energy or radiation. An antenna or dish focuses the beam and it travels through the atmosphere. Anything the beam hits is what we call a target. That target scatters radiation back to the radar dish, some straight back to the antenna. This reflected radiation is then measured, and you can basically figure out distance with speed that the beam travels at and the time that process takes. Properties of these targets that we're interested in, the amount of energy reflected back is called reflectivity. Reflectivity depends on the number of targets in an area and their size. Some problems with that include those like a few large drops can reflect the same radiation as a bunch of smaller drops. That's why radar is not an accurate tool for measuring rainfall, but really just identifying where it is. Doppler radar is one of the ones that we use pretty regularly. Doppler radar is the meteorologist's window into observing severe storms. We have about 159 radar towers across the United States. NOAA's National Weather Service has comprehensive coverage of the continental United States and partial coverage of Alaska, Hawaii, Puerto Rico, and Guam. Doppler radar detects all types of precipitation, the rotation of thunderstorm clouds, airborne tornado debris, and wind strength and direction. That reflectivity shows the location and amount of reflectivity on a display. It's basically what you see on TV. We'll see an image of it here in a second. Velocity images are what we call the product of Doppler radar. This shows the component of wind towards or away from the radar and is useful for detecting rotations and damaging winds. So for reflectivity images, we'll see on the next slide here, color scale tells you what the image means. You can tell if the returns are light, moderate, heavy, or severe. Earth curves away from the beam, so you see below clouds closer to the radar site and above clouds farther away. And further away, you get less resolution as the beam that is being used to measure this spreads out. So here you can see a typical reflectivity image. One thing you can notice is it's always cut to kind of this, and let's see it here, circular pattern that we see kind of right around here. So the central point, this would be likely from Des Moines, and we can kind of see this circulating pattern around here. For velocity images, again, color scale is important. Wind towards the radar are usually negative. Wind away from the radar is usually positive. There are limitations, however, to the maximum wind speeds that you can detect. In the event of very strong winds, you can get velocity or range folding, where it basically goes off one extreme end of the scale and onto the other. So the high then becomes an extreme low. So here's a typical velocity image. So you can see speed here in knots. Now the next step in radar development is what we call the phased array radar, or PAR. This project was established to demonstrate the potential of potential to simultaneously perform aircraft tracking, wind profiling, and weather surveillance with a single phased array weather radar. NOAA's National Weather Radar Test Bed, or NWRT, was a repurposed U.S. Navy Spy 1A phased array radar built in the 1970s and tested and evaluated in Norman, Oklahoma. Current weather radar mechanically rotate and tilt the radar dish to sample different parts of the atmosphere. A phased array has a unique flat panel antenna that remains stationary. The panel is made of a grid of fixed antenna elements that we can kind of see in this picture here. Each of them transmit and receive a signal. As a result, the radar beam can be steered electronically, giving users the ability to control how, when, and where that radar is scanning. This means the radar can be controlled to direct its beam only where storms are detected. Focused observations of storms lead to faster updates since the radar does not have to waste time scanning clear air regions. PAR can scan the sky in less than a minute, revealing critical weather thumbprints that point to the potential of severe weather. Radar scans every minute will make severe weather easier to confirm, making warnings more accurate and reducing false alarms. Forecasters will also be able to watch changes in the storm to know when it is strengthening or weakening. Scientists have already learned more about thunderstorms with PAR data, and an independent study estimates implementation of a combined PAR network of radars satisfying both the Federal Aviation Administration and National Weather Service missions to save taxpayers $4.8 billion over the entire life cycle of the radar. So how does it work? Well, unlike conventional radar, they use multiple beams, multiple frequencies, and can control things basically electronically. The advantages: up to 6 times faster scanning atmosphere. They can track multiple targets, so several storms at once. And they can potentially increase warning lead times from 12 to 22 minutes for tornadoes. Satellites is the next big one. Weather satellites monitor Earth from space, collecting observational data that NOAA scientists use. NOAA operates 3 types of weather satellites. So polar orbiting satellites orbit the Earth close to the surface, taking 6 or 7 detailed images a day. Geostationary satellites stay over the same location on Earth, high above the surface, taking images of the Earth as frequently as every 30 seconds. And then deep space satellites face the sun to monitor powerful solar storms and space weather. NOAA also uses data from satellites operated by other agencies and other countries. Radiosondes are our primary source of upper air data. At least twice per day, radiosondes are tied to weather balloons and are launched in 92 locations across the United States. You can kind of see what that looks like in this picture here. So in its 2-hour trip, the radiosonde floats to the upper stratosphere where it collects and sends back data every second about air pressure, temperature, relative humidity, wind speed, and wind direction. During severe weather, it's usually launched much more frequently to collect additional data about the storm environment. Automated Service Observing Systems, or ASOS, constantly monitor weather conditions on the Earth's surface. More than 900 stations across the U.S. report data about sky conditions, surface visibility, precipitation, temperature, and wind up to 12 times per hour. Nearly 10,000 volunteer National Weather Service cooperative observers collect and provide additional temperature, snowfall, and rainfall data. The observational data that the ASOS and volunteers collect is essential for improving forecasts and warnings. NOAA's Weather and Climate Operational Supercomputer System, or WCOS, is the backbone of modern forecasting. With 5.78 petaflop computing capacity, it can produce quadrillions of calculations in a second. Their supercomputers are almost 6 million times more powerful than your average desktop. Observational data collected by Doppler radar, radiosondes, weather satellites, buoys, and other instruments are fed into computerized National Weather Service numerical forecasts. The models use equations along with new and past weather data to provide forecast guidance to meteorologists across the United States. Then we've got our AWIPS, what we mentioned a little bit earlier. NOAA's Advanced Weather Information Processing System. This is a computer processing system that combines data from all the previous tools that we talked about. into a graphical interface that forecasters use to analyze data and prepare and issue forecasts, watches, and warnings. This system uses NOAA supercomputers to process data from Doppler radar, radiosondes, weather satellites, ASOS, and other sources using models and forecast guidance products. After meteorologists prepare the forecast, AWIPS generates weather graphics and hazardous weather watches and warnings. All this helps meteorologists create more accurate forecasts faster and better than ever before. So, as a recap, this is kind of all we talked about is what goes into making a forecast. It's not just looking at some charts or maps and kind of coming up with a prediction. It takes a lot more than that, a lot of very, very advanced equipment to kind of make these forecasts realistic and accurate, which really goes to improve the safety of the public and safety of the infrastructure and buildings that we live in and use. So that's the recap for this video. In the next one, we're going to talk about weather folklore. It should be a shorter video and maybe a little bit more fun. So I hope you enjoyed this one. We'll see you in the next video. Thanks.